All right. Good morning, everyone. I guess we should.
Oops, sorry.
You should stay.
Okay. I was trying to get out.
No, we should get started to keep everything on time. So, welcome to the RowHammer session. My name is Matan Erez. I'm a professor at UT Austin, and we have three great talks. All of them from students of former UT graduates, so it's going to be great. Our first speaker is Giray Yaglikci. He's PhD candidate at ETH Zurich. He works with Professor Onur Mutlu. He's interested in DRAM robustness and performance. Finishing up his dissertation very soon. He's going to be in the job market in a few months, from what I understand, and interested very much in DRAM, read disturbances, and that's what we'll hear about today.
Thank you very much. Hello, my name is Giray Yaglikci, and I'll be talking about our paper, Spatial Variation Aware Read Disturbance Defenses today. But before I start, I want to mention a fundamental primitive of security and privacy called memory isolation, or in a much realistic sense, it's lack of memory isolation. So imagine you have memory and you access a region in this memory, and your access causes some bit flips in other regions of this memory that you didn't access. When such thing happens, it can lead to data loss or corruption. It can compromise application correctness. It can be used to leak private data, and it can be used to take over even computers. So the principle of memory isolation dictates that an access to one memory address should not have unintended side effects on data stored in other accesses. Unfortunately, it's not really easy to ensure memory isolation in modern memory chips. And this is why. So this DRAM is the prevalent memory technology. And in DRAM, we have a phenomenon called read disturbance. You read a memory location, and then it can disturb data nearby and induce bit flips in nearby locations. A little bit more background into read disturbance. Inside DRAM, we have accesses in a DRAM row granularity. So you want to access data, in this example, located in row 2. You first need to open this row, and then you access data. And then once you want to access another data in another row, you need to close this row. So when you repeatedly open and close this row like this, you have bit flips in nearby rows that you didn't access. And this phenomenon is called RowHammer. It's a prime example of DRAM read disturbance. The row that we keep accessing is called aggressor row, and the rows that are affected are called victim rows. And RowHammer can be used for breaking memory isolation. There's another recently discovered DRAM read disturbance phenomenon, row press. In row press, you open a row, and then you just wait. And then after a while, you see bit flips in nearby rows. So this was also published in last year ISCA. You can go check the paper. This is also used in breaking memory isolation. Today, I want to focus on the variation of read disturbance vulnerability across different DRAM rows. In this cartoonish picture, imagine that all your DRAM rows are represented in this box. To induce a read disturbance bit flip, one should access a row several thousand times for a small fraction of DRAM rows. And for the vast majority, you need like tens of thousands of activations. And for some other small fraction, you need to access like more than 100,000 times. And we named this variation as like spatial variation and read disturbance vulnerability across DRAM rows. Today, we configure our read disturbance solutions based on the worst case, based on the thresholds of the most vulnerable rows. However, not all rows need the same level of protection. And this leads read disturbance solutions to overprotect some rows and incur large performance overheads. So with this, I will quickly summarize the rest of this talk. In this paper, our goal is to understand the spatial variation in read disturbance across DRAM rows, and to leverage this understanding to improve the existing read disturbance solutions. To this end, we conduct an experimental study on 144 real DDR4 DRAM chips from 3 major manufacturers, and we characterize all rows in a bank and 4 banks in a chip. And we end up with the takeaway that read disturbance vulnerability significantly and irregularly varies across DRAM rows. With this takeaway, we propose a new mechanism called SVARD. SVARD is Spatial Variation Aware Read Disturbance Defenses. Seward dynamically tunes given disturbance solutions aggressiveness to the victim row's vulnerability level dynamically, so it reduces the performance overhead. Seward can be implemented either in the memory controller or in the DRAM chip. We evaluate Seward's performance, and we show that it greatly reduces the disturbance solution's performance overhead and significantly improves system performance. So let me quickly define our motivation and problem. So technology scaling shrinks DRAM cell size and cell-to-cell spaces, and this exacerbates DRAM disturbance. And in a way, you can see in the recent papers that in the last decade, there is more than 2 orders of magnitude reduction in the minimum hammer count that you need to perform to induce the first read disturbance bit flip. And DRAM chips are increasingly more vulnerable to read disturbance with technology of scaling as chip density increases. And to cope with that, existing solutions need to behave more aggressively. And since they overprotect many rows, it significantly increases their performance overhead. So the question is, can we leverage the variation in read disturbance vulnerability across DRAM rows to reduce the performance overheads of these mechanisms? But the problem is that, unfortunately, no prior work rigorously studies this variation and its implications on future solutions. So our goal in this work is to empirically understand the spatial variation in read disturbance across DRAM rows, and to leverage this understanding to improve the existing read disturbance solutions. To this end, we conduct an experimental study on our FPGA-based setup program with DRAM Bender, which is open source. You can use it yourself as well. That provides us with fine-grained control over DRAM commands, timing parameters, and temperature. In this study, we test 144 DRAM chips in total from 3 major manufacturers that cover several densities, die regions, and chip organizations. And our takeaway of this study is that read disturbance vulnerability varies significantly and irregularly across DRAM rows. Here, there's a histogram where on the x-axis, we have minimum hammer count to induce the first bit flip, and on the y-axis, we have the fraction of DRAM rows. So different colors identify data from different DRAM modules from a particular manufacturer S in this case, Samsung. And the error bars show the variation across banks in the distribution. So when we look at the smallest value here, which is the worst value for the minimum hammer count to induce the first bit flip, HC first, this is the value that we see across these 5 modules, the minimum one. And when we look at the distribution of these HC first values across rows in every module, we see a wide range of values here from 12K to 128K. So we conclude that the minimum hammer count to induce the first bit flip significantly varies across DRAM rows. And when we look at this analysis across DRAM modules from other manufacturers as well, we observe the same thing. And we have more detailed information in the extended version of the paper. We provide more detailed results, so you can find it on archive. I will later on share a QR code as well in case you want to scan. Next, we look at the regularity of the distribution across DRAM rows. So on the x-axis, we have the DRAM row addresses now, and on the y-axis, we have the minimum hammer count you need to perform to induce the first bit flip or HC first. And it's just like all around, and there's no visible or easily visible regularity in HC first based on the row location. And this is true for DRAM modules from all 3 manufacturers. So to go deeper, we also measure the predictability of read disturbance vulnerability based on the row spatial features. And we use the spatial features of bank address bits, subarray address bits, row address bits, and rows distance to the local row buffer. And in our methodology, we cluster DRAM rows into 15 different categories of read disturbance vulnerability level. And we predict whether a row belongs to a particular cluster or not by using the spatial features that we define above. And we measure the F1 score of this predictability. And we saw that the F1 scores do not look great, actually. And there's only like a few features that can exceed an F1 score of like 0.7 only for manufacturer S. Since we cannot generalize this predictability across manufacturers, we conclude that spatial features are weak predictors for the row's read disturbance vulnerability. So we conclude that read disturbance vulnerability significantly and irregularly varies across DRAM rows. And there are more results in the paper, of course. You can check. So with this experimental takeaway, our key idea is to leverage the variation in read disturbance vulnerability across DRAM rows so that we can improve the existing read disturbance solutions. To this end, we propose a new mechanism called SVART, spatial variation aware read disturbance defenses. So it dynamically tunes the aggressiveness of an existing solution to the victim row's read disturbance vulnerability level. And what it essentially does is that it performs fewer preventive actions, such as performing preventive refreshes to a victim row if the victim row is less vulnerable to read disturbance. By doing so, SVART significantly reduces the performance overhead of existing solutions. And SVART can be integrated in many existing read disturbance solutions. I will give a short example using para probabilistic row activation. So I will just briefly explain how para works itself. You have a row activation. Para generates a random number, and it compares the random number against the threshold. And if the random number exceeds the threshold, then it preventively refreshes the victim row. And it gets the victim row information from the row activation because it's the adjacent row to the aggressor row. And when we integrate with SVART, SVART gets the victim row ID. And it uses the profile from the experimental characterization. And it adjusts the threshold, tune the threshold dynamically based on that. So in a sense, if the victim row is less vulnerable to read disturbance, then SVART applies a higher threshold, and it leads to fewer preventive refresh operations. And the opposite also correct. If victim row is more vulnerable, then the threshold gets reduced, and then the preventive refreshes will perform more aggressively. So this way, SVART dynamically tunes para's threshold to the victim row's vulnerability. So I will not get into details, but SVART can be similarly integrated with other read disturbance solutions as well, such as RowHammer, Hydra, RRS, and Aqua that we try. So SVART needs to manage some metadata to do all these. It classifies DRAM rows into several vulnerability bins. For that, it needs to maintain a few bits for each DRAM row. And it needs to be implemented where the existing read disturbance solution is. So it can be implemented in the memory controller or in the DRAM chip. If it's implemented in the memory controller, we can store this metadata in some SRAM table in the memory controller or among some data integrity bits in the DRAM chip. Or if the implementation is in the DRAM chip, then we can put data inside each DRAM row, or we can store them in a separate DRAM array as well. So we explore different integration and implementation methods in the full paper. I will refer you to there for more details. Let's go with the performance evaluation. So we conduct cycle level simulations using Remulator. We simulate the system with 120 different 8-core multi-program workloads from different benchmark suites. And we integrate SVART with 5 different mechanisms: Aqua, RowHammer, Para, Hydra, and RRS. And we sweep some futuristic minimum HC first values, the minimum hammer count needed to induce the first bit flip. We start from 4,000, which is like very realistic today. And we go down to 64 to project for the future DRAM chips. Here is the performance results of Para. On the x-axis, we have the minimum hammer count to induce the first bit flip. On the y-axis, we have system throughput in terms of weighted speed up. And as DRAM chips get more vulnerable, it's not surprising, Para incurs larger performance overheads, and the system throughput gets lower. So we integrate Para with SVART using 3 different vulnerability profiles that we gathered from real DRAM chips. This is from H1 Hynix, Micron, and Samsung. And in all of them, we show that SVART can reduce the performance overhead that Para inflicts on a system. And by doing so, it improves system throughput by up to 95% in this case. And these are the performance results from other 4 mechanisms that we simulated. And we observe similar performance overhead reductions and system performance improvements in these existing solutions. So we have more analyses in the paper, but I will not get into details for the sake of time. So we have we analyzed the spatial variation in read disturbance bit error rate across DRAM rows as well. We looked at the spatial variation of row press. We provide more algorithms and details into our experimental study. We have a reverse engineering methodology that we share to identify the subarray boundaries. We discussed different implementation methods of SWART in memory controller-based implementations or on DRAM die. And we also looked at the hardware complexity of SWART and showed that it can be implemented at low cost with no additional latency on the memory requests. In addition to these, we also did a preliminary analysis on the effect of aging on DRAM read disturbance. And we observed some effect of aging that can reduce the minimum hammer count you need to induce the first bit flip over time. So it begs more rigorous studies for effect of aging, and also it motivates that there's more studies needed for online profiling of read disturbance vulnerabilities. And you can find all these details in the paper. To conclude, we present the first rigorous experimental study on spatial variation of DRAM read disturbance across DRAM rows. We tested more than 100 DRAM chips from 3 major manufacturers. We characterized all rows in a bank, and we looked at 4 different banks. And we observed that read disturbance vulnerability very significantly and irregularly. And we proposed a mechanism to leverage this observation. The mechanism SWART dynamically tunes the solution of aggressiveness, solution's aggressiveness to the victim row's vulnerability. And it can be implemented in the memory controller or in the DRAM chip. And we show that it significantly reduces the performance overheads of existing solutions. And we hope and expect that SWART may present itself to any worthy read disturbance solution. And with that, I'm done. Thank you very much, and I'm happy to answer your questions.
Okay, we have time for a couple of questions. If you please use the microphone and state your name and affiliation.
Hi, this is Rohan from SK Hynix. First of all, it is my personal opinion, not the official opinion of my company. And you compare many mitigation solutions for RowHammer, but as you might know, there is a new standard for RowHammer mitigation, which is RFM,
Yes. Yes.
So why didn't you compare RFM for performance over?
Yeah, so in the study, we didn't evaluate RFM, so I don't have a result to show you. But we expect some similar results with RFM as well, because it's basically tuning the aggressiveness, right? So for RFM to work, you need to have a read disturbance solution inside your DRAM chip, and you can tune the aggressiveness of that DRAM chip because it also works with thresholds in a similar way to these mechanisms. Does that answer your question?
So you're saying you have numbers in the paper regarding RFM?
Excuse me?
So can I find the performance degradation of RFM in the paper?
Yeah, in this paper, we do not have it. In an extended version, probably we would put it. We also evaluate it in some other papers that are coming up, but I hope you will have it soon.
Thank you.
Hi, thanks for your stuff. And I'm going to keep from Spatial Electronics. And your question is to say the minimum count of HPCA which can incur bit flips for each of the across the bank. So what I mean is that my question is, what's the reason that a different minimum bit flip count for each across the band? What's the exactly reason? Have you found that?
The reason of the variation across rows?
Yes.
So we do not know the root cause, of course, but there is probably a large impact of the manufacturing process variation. And also, when we look at the how bit error rates change, actually, we see some repeating patterns over there, and we speculate that they can be due to, like, when you get closer to the subarray boundary, the behavior changes a little bit. So your bit error rate like reduces and increases again. So there can be some like design-induced variations as well. So, but these are all speculations, so we do not know the root cause because we do not know what is inside the DRAM chip. You know better, probably. Thanks.
Okay, one more quick question. Peter joined from Limitation. So I was wondering if you could elaborate more on this aging phenomena and if you saw that the distributions would change or you would see other interesting emergent behaviors due to aging, or was it just that the amplitudes and the occurrences would increase, but the overall, like, it would change in magnitude, but not in shape?
Yeah. So first of all, there's a disclaimer. This is a preliminary data. That just like this is not proper accelerated aging or anything. We just like kept hammering some chips for 68 days, and we compare the HC first values that we found before aging and after aging. So on the x-axis there's before aging, on the y-axis after aging, and you can see that for a small fraction of DRAM rows, we observe some significant reduction after this process. So this is actually just like a motivational data for a more rigorous agent study.
Okay, and then this would be only for some rows, and then other rows would not observe this. You would hammer other rows, and they wouldn't increase as much.
So I would say like we did not observe for some other rows, but they can also get affected. So I cannot say for sure that they will not get affected from aging. Yeah, thanks.
Thank you, Giray. One more time.
Thank you.